All right. Today we're going to be talking about water hammer and surge tanks, which are two related topics. And just as the reminder about homework 5, that'll be due on Wednesday the 16th, and I noticed that the graders already gone in and started scoring some of the homework 4 assignments, and so I expect those will probably be finished over the weekend. Any schedule questions or general questions before we move on to water hammer and surge tanks? All right, well, let's look at a couple of videos to set the stage about this issue of water hammer and surge tanks. The first is a video of someone at their kitchen sink. So let me just dim the lights a little bit here so it's easier to see. And there's some sound too, so hopefully it won't be blasting too loud. Let's see here. All right. If washing the dishes wasn't already annoying enough, right? Imagine that every time you get a drink of water or try to wash a plate. So the water was flowing fine, and then he started closing the valve, and we saw that kind of repeated hammering sound. It's not always repetitive like that, but in that case, the water hammer was reflecting back and forth between the reservoir and the valve. And we'll talk about that reflection action and why that's significant, and how travel time between 2 points is an important factor. But just to look at one other video, now this is an oldie but a good one. We'll have to suffer through the commercial, I think. Okay. So you can tell this is from the VHS age. Let me switch off the closed caption. This is old-timey video.
Shock occurs when a valve is closed too abruptly. When a water valve is open, a solid column of water moves from its source at the main to the valve outlet. This could be 100 pounds of water flowing at 10 feet per second or above.
So why did he say 100 pounds of water? That's just however much water. I better start the recording here because this is an important point. It was already going. Okay. The 100 pounds of water that's mentioned in there would just be however much water is in the pipe between the valve that's being closed and the reservoir that the water is coming from. So maybe it's coming from a tank on the roof of an apartment building. Maybe the water is coming from a really large pipe somewhere at a trunk line, or it could be a reservoir on a hill that's providing pressure to the pipe network in a town. But just this idea is that there's a certain weight of water in the pipe and it's moving, has momentum, and it's going to be stopped suddenly. So this whole phenomena that we're talking about, water hammer, is related to the weight of the water in the pipe, the fact that the water is moving, and when it stops suddenly, it causes an increase in pressure. And so you're beginning to get the idea that it has to do with the either suddenness of the change of velocity of a water column flowing through a pipe. Think about if you're driving a car and the car's velocity stops suddenly because you run into a coal truck versus if you apply your brakes. You're going to have a very different experience in those two extremes. And so in the case of the water can be slowing down gradually as the valve is closed slowly. And we saw in the video there, this was some pretty high-tech stuff back in the 80s, these paper graphs with a little pen on there. Everything would be digital now, but you saw that when the valve is closed instantaneously, that this little pen, which is a measurement of the pressure, goes really high. In fact, we're going to learn how to calculate the magnitude of how high the pressure goes The valve that was closing here, just taking it a quarter turn, instantly closed it. And so, these globe valves are particularly dangerous for hydraulic shock, whereas a gate valve, which you have to crank probably, I don't know, 20 or 30 times to finally get the gate all the way down into the pipe, you're very unlikely to have water hammer from a gate valve. But other types of valves are more dangerous, and especially when they're mechanically closed rather than closed by hand. And so, mechanically closed valve, when they're preparing the instrumentation and the controls for a water treatment system, they pay careful attention to issues like this to limit these big increases in pressure. 600 psi very well could be enough that it ruptures a welded joint downstream, or it could cause a water heater to explode. Any place where there is a sensitivity to a rapid onset of pressure. But if we look at the slow closure of that valve, where it's being just kind of gradually closed, the needle didn't move hardly at all, because the water had an opportunity to slow down, and there's less pressure accumulation. And there is a pressure wave that's still reflecting from that closed valve back to the reservoir and back to the valve again, but it has such an insignificant increase in pressure that it really wasn't even measurable. So I'm going to step through kind of the theoretical reason why water hammer can arise, and we'll look at this diagram that's provided in the text as a guide. And in the first case, if we're in a steady flow situation where water's coming from a reservoir and going through a pipe, let's look at some of these lines here. The delta Z is just some elevation above a datum at any point in the pipe. And it doesn't matter if the pipe is horizontal or if it's downward inclined or upward inclined. All different pipe orientations are sensitive to water hammer. And so this is showing it at a slight incline just to make the case that it doesn't necessarily have to be horizontal for a water hammer to arise. The other thing that's important to point out is H sub F. And so from the H sub F decreasing in the direction of flow, that's what implies to us that the velocity is from the reservoir through the pipe to the right. And so the water's flowing freely, and we're going to zoom in on a certain control volume because we will apply the momentum equation, which you may remember from fluid mechanics, that some force will arise when there's a difference between the inflow and the outflow velocity within a control volume. And so we've got some flow rate, Q, of a liquid that has a density. And if you multiply density and volumetric flow rate together, remember that we have mass flow rate, m dot. So mass flow rate is density times volumetric flow rate. So there's some flow rate of water going through the pipe, and if you multiply mass times velocity, that's momentum. And mass times the difference in velocity is the change of momentum that causes an increase in force. And the force that's going to be applied is applied over the area of the valve. And so pressure is force divided by area. So a change in velocity causes a force. The force is expressed over an area, the area, cross-sectional area of the valve, which is normal to the flow of the water through the pipe. And once the valve is closed, suddenly what happens is that the water near the valve stops first. Now, water is incompressible, we say. The truth is, it's a little bit compressible. There is a bulk modulus of elasticity for water that's very, very high, but water is a little bit compressible, and that's part of the reason that water hammer occurs. And it's one of the things we'll have to take into account when we calculate the increase in pressure that happens when we close a valve too quickly, is we'll take into account, well, exactly how compressible is water compared to, for example, the compressibility of the pipe. Because what's happening is that the water is compressing closest to the valve at the same time that the pipe is expanding a little bit. Because the increase in pressure right near the valve is causing the pipe to swell. So think about if the pipe is made out of lead or steel or whatever the case may be, it's going to expand very slightly because of that pressure increase. And closest to the valve, the water velocity is 0. But if you get further away from the valve, the water hasn't stopped yet. Although it's pretty close to incompressible, it's not strictly incompressible all the way. And so some of the water in the pipe is still moving, even though right at the valve the water stopped. So the pressure is building, the energy is accumulating. As the pipe expands, there's some stored energy in that. What was previously the kinetic energy of the water flowing through the pipe has been transmitted into some increased potential energy of the pipe expanding. And the wave of pressure is going back away from the valve at a velocity that we called celerity. C, celerity. And so there's a temporary increase in the amount of energy at the valve. Whereas before, when the water was flowing, there was less energy at the valve than at the reservoir. Look how the elevation of the total energy line is lower at the valve than it is here in the reservoir. In the reservoir, the total energy line is just the elevation of the water. So when the water's flowing, there's less energy at the valve. That's why the water's flowing from the reservoir towards the valve. But when we instantly close that valve, temporarily and briefly, there's more energy at the valve than there is anywhere else. So that's what's causing this pressure wave to flow from the valve back towards the reservoir. I've already talked about how the pipe expands and the water compresses, and that's how the shock wave is transmitted. There's a certain point at which finally there isn't water entering the pipe anymore. It's not flowing towards the right. This wave of increased pressure goes through the entirety of the pipe, and there's a certain kind of a turnaround point when the shock wave is all the way to the reservoir, where the pipe has expanded as much as it's going to, and the velocity of the water in the pipe is 0. And so this delta H just represents how much extra energy is stored in the pipe right now because of its expansion. And now, because there's more energy in the pipe than in the reservoir, that's going to force some of the water in the pipe to flow towards the reservoir. So you'll notice now the velocity is going away from the valve towards the reservoir. In the pipe section that is still expanded, the velocity is 0, but it's kind of like, think about water in one of those really long balloons, the kind that they do like animals with. If there was water in a really long balloon, when you open up the end of the balloon, some of the water is flowed out. The part of the balloon that still has water in it and still is expanded, the water velocity is 0 in that section, but the portion of the balloon that is contracted is what's providing the water in the direction of the opening. So that's what's being depicted here, is the water flows to the left, and now the shock wave is going back the other direction, towards the valve again. So the water flow and the shock wave flow are going in opposite directions, and this shock wave is headed back towards our valve, which is still closed. And so that is what accounts for, in the video we watched, when the person was closing the faucet at the sink and how it was kind of stuttering a little bit. The shock wave the valve wasn't all the way closed yet, but even just the part that had been closed was sending kind of this reflecting shock wave back and forth. And I think probably that valve may be like a little broken. I doubt that it was always like that from the beginning of when it was installed. But this wave reflection phenomena is what we need to quantify. We have to calculate the velocity of this shock wave. We have to know the length of the pipe that we're dealing with. The fluid properties like its density and temperature come into play because those will influence the compressibility of water. We also have to know about the pipe, what kind of material it's made out of and its thickness, because those things will also influence the celerity of the shock wave. So let's talk about the compressibility of things. Bulk modulus of elasticity is a way of describing how compressible a fluid is. And it's a fluid property that varies depending on what the liquid is. It varies based on temperature. But what it is the change in unit volume for some increase in pressure. So let's say that the pressure is going up. An increase in pressure is going to decrease the amount of volume that's occupied by a certain quantity of water. So that's what we interpret of this negative sign here. And these tables show in traditional units bulk modulus of elasticity for water in terms of pounds per square inch. You can see this is a very, very high constant, which implies that incredibly large pressures are required to have even a small minimal decrease in the volume occupied by a certain quantity of water. Your textbook also has the bulk modulus of elasticity in SI units, although it says it's these units divided by 10 to the ninth. It's actually these units times 10 to the ninth newtons per meter squared. But what you can see is that as the temperature increases, so does the amount of pressure required to compress water. It becomes more difficult to compress with an increase in temperature. And so celerity is that velocity of the pressure wave. And in an infinite extent, out in just unconfined water, let's say in the ocean, how quickly does a shock wave of energy travel? It would be dependent on the bulk modulus of elasticity and the density of the fluid. So a typical water velocity, a typical velocity of a shock wave traveling through water would be around 1.4 kilometers per second. And that's if you have open water in all directions. But when we channel water through a pipe, through a conduit, it slows down the shock wave. And how much that celerity decreases is dependent on the ratio of the diameter of the pipe to the thickness of the pipe walls, as well as the ratio of the bulk modulus of elasticity for water and the bulk modulus of elasticity for the pipe. Because remember that the water's compressing and the pipe is expanding, and that change of size is going to affect how quickly the water travels through the pipe. So it slows things down. The water being compressed, the pipe expanding, and the ratio of how much it slows down can be estimated. Now, just as a note, we have to, as always, be sensitive to the units. And so if you have a pipe diameter given in inches, then you'd need to express the thickness of the pipe walls in terms of inches as well. Even if your bulk modulus, for example, is in newtons per meter squared, you could use millimeters for both the pipe wall thickness and the pipe diameter, because it's a ratio in the numerator and the denominator. As long as these two length parameters are in the same units and the bulk modulus of both the water and the pipe are in the same units, then everything's going to cancel out. You'll have in the denominator a unitless expression, whereas celerity is going to have length per time, so meters per second, feet per second, and so on. Any questions so far about what causes water hammer or how we can estimate the speed of the shock wave? So water's going from a valve that gets closed too quickly towards a reservoir and then back to the valve again. So the applicable travel time that we have to be aware of is twice the pipe length divided by the celerity. And I guess maybe just to clarify that, we're talking about the celerity of the water in the pipe, not the theoretical celerity of water an infinite extent. So we want to know for this particular pipe, how quickly will the shock wave go through there? We want to know how long the pipe is. And long pipes are more dangerous than short pipes. So think about, why would a long pipe be more dangerous? It's because what we're going to be calculating is what's the minimum amount of time that should be taken to close the valve. So if you close the valve really slowly, you're never going to get into trouble. Like, if you schedule an hour and you're just closing this valve very slowly over the course of an hour, you're never going to have water hammer. But you're not going to want to waste all that kind of time, so you'll progressively start closing it quicker and quicker and quicker. But there is some minimum point below which you're going to have a maximum increase in pressure. And so the magnitude of how bad could the pressure wave get, it's the initial velocity times the celerity multiplied by the density of the fluid. And if you close the valve in less time than this, T sub L, then you will experience the delta P, the maximum delta P. If you close the valve a little bit slower than this T sub L, the pressure is still going to increase, but it won't increase as much. I'll show you a formula in a moment where we could calculate what is the pressure increase if we don't close it all the way as slowly as this critical time implies. Let's test this set of equations out with an example. So let's say that we have a pipe that is 2,000 feet long. Now that's its physical length. Remember that when we calculate the travel time, we have to double that physical length. So L is 2,000. D, the diameter of the pipe, is 4 inches. The thickness of the pipe, 0.2 inches. We have the pipe modulus of elasticity, the water modulus of elasticity, the water density, and here, working in traditional units, the density you're going to need is 1.94 slugs per cubic feet. I've mentioned slugs before. Oftentimes when we're talking about unit weight, remember, the unit weight of water is 62.4 pounds of force per cubic foot, but that's force per volume. Here we're talking about density per volume, which is 1.94 slugs per cubic foot. So you can just use this density down here when we calculate the delta P. But we are going to have to keep track of any changes of other units along the way, because the delta P that you're going to calculate will be pounds per square foot, and I'm asking you to calculate what's the pressure increase in PSI. Okay, so in part A, you're going to need to first calculate the velocity of the water, the initial velocity of water through the pipe, the theoretical celerity, the celerity of the water in the pipe that we're talking about, and then the maximum pressure increase that could occur if we close that valve instantaneously. And by instantaneously, I mean in less than the T sub L. And then for part B, you're just going to calculate what is T sub L. All right, let me pause for a moment and let you start plugging away on the calculator. Did everybody else already get the theoretical wave celerity of 4874 feet per second? We need to convert the given modulus for the water of 320,000 pounds per square inch into pounds per square foot. And so you have to multiply by 144 to get pounds per square foot. And then we'll divide by the 1.94 slugs per cubic foot to get 4874 as the theoretical velocity. So you'll notice that the celerity of the wave in the pipe is significantly less than the open extent celerity, 4874 feet per second versus 4397. And so the pressure change is going to be 58,649 pounds per square foot, which translates into 407 psi. And in terms of travel time, what we're talking about is the 2,000-foot round trip multiplied by 2, and then divided by the velocity of the shock wave through the pipe. So the round trip travel time for that shock wave is 0.91 seconds. I see people taking notes, so I'll give you a moment. I'll pause here. Are there any questions? Other questions? So that's the worst case scenario. The worst case scenario is 407 psi pressure increase. If the valve is closed in less than 0.91 seconds, then that's the pressure wave increase that we'll see. But what if we close the valve slower than that? Do we get off scot-free? The answer is no. If we want to find the pressure increase that's going to occur, it is a function of the initial pressure before the valve was closed multiplied by some empirical function which is trying to estimate the relative effect of the valve closure time that you're using and the length and travel time, the speed of the water initially. So I just wanted to illustrate briefly, let's say in that previous example, if we had a typical water system which is around 70 psi, and if we closed it at 1 second instead of 0.91 seconds. So we already know what the pressure increase will be. If we close it at 0.91 seconds, then the pressure increase is going to be 407 psi. So what if we take an extra 9/100ths of a second, so 1.0 seconds instead of 0.91. So we could put it into this formula, calculate n, then substitute that in here. And let me just show you that briefly, the calculations for that. If we use this same situation as the previous example, but we're saying that the initial pressure before the valve was closed was 70 psi and a 1 second valve closure time, I can calculate the n term based on all the data that we've got. And it turns out that the pressure increase would be 239 psi instead of 409, which was the increase in pressure if the valve is closed in less than 0.91 seconds. So if you close it in 0.1 second, 0.2, 0.3, you get the same pressure increase. 0.9, same pressure increase. But then once you go close the valve slower than that round trip travel time, the pressure increase is going to be less than the maximum. And here we see what it would be if we closed it in 1 second. So you could create a table that shows what's the pressure increase going to be, and a designer would look at what kind of a pressure increase is suitable or appropriate or can be tolerated based on the quality of the pipe, the quality of the valves, and from that they'd estimate how slowly can that valve, how slowly can we get away with closing a valve. Okay, so the only other thing I wanted to tell you about today is surge tanks. And these can be used as one way of relieving the increased pressure, because when you close a valve, rather than having the pipe expand and the water start to flow the other direction, if instead that excess water goes into a relief area and the water level just increases, then it's a way to prevent the buildup of pressure in the pipe. So we can calculate how quickly, or excuse me, how high the water level will rise inside of some sort of a relief tank by taking into account the pipe length, the cross-sectional area of the pipe, the cross-sectional area of the tank. And so this little example is just, taking our previous scenario a little bit further, saying What if we wanted to prevent any kind of possibility of water hammer by installing a tank that has an unknown diameter, but we're allowing the water level to surge up to 1 foot? So if we could tolerate a water level rise in some sort of a surge tank of 1 foot, then how big would the tank need to be? And so to estimate that, what this formula allows us to do is just rearrange the equation. Instead of solving for the maximum surge height, that now becomes a known 1 foot. So we could rearrange it to solve for what would be the cross-sectional area of the tank that's required. And then if we know the relationship between area and pipe diameter, then we could find the required diameter of the pipe that's needed. So these surge tanks are just a way of, I think in the video we watched they called them arresters. It's kind of like a shock absorber, and a surge tank can prevent a lot of problems. And all right, so that's all the time we have for today. It's Friday afternoon. I think you've got other things to do. Just remember that homework 5, that's due on Wednesday the 16th. It includes Hardy Cross, then also some problems related to water hammer.